Hello, welcome to our lesson on radicals. You can also think of this as rational exponents. We'll get to that connection. This is our final lesson in the review portion of the book. So next week we'll be moving on to some new horizons. Radicals. Well, these are roots. You may have heard of it that way before. Let's talk about the nth root of some number b. It's this funny bracket looking sign. And I'm going to put a little n there. This represents the index, the type of root we're taking. And let me put an arrow this way. This bracketed thing we call the radical. And then we have our b inside. We're taking the nth root of b. Let's call it some number a. What this means is b is a number such that, or with the property, that b is equal to a to the n. We do need to add a little bit of nuance to this. If two roots, because under this definition there can be two answers, sometimes we'll see. If two roots choose the positive number, we want just one answer with these. Before I start doing some examples, quick note on notation. If you're taking the second root of something, which we call the square root, we omit the 2, because this is the most common type of root, so we don't like writing 2's all the time. If the number is omitted, then it's really a 2 hidden there. Let's do some examples. Part A, we will take the cube root of 27. And when there's an index of 3, we say cube root, just like when we say x cubed. The answer is 3, and this is because if you think about it backwards in terms of exponents, 3 cubed is 27. And now to be extra clear, this 3 is the same as this one. So we have a couple 3's floating around. And why not? This index 3 is the same as this power 3. Part B, pretty similar. But now it's the cube root of negative 27. Now, if you've learned about radicals before, you might be a little nervous seeing a negative inside, which pretty good instinct, and I'll talk about that in a bit. But it turns out in this case, this is fine. So the answer is negative 3. And this is because if you cube a negative 3, you will find that this indeed gets you a negative 27. So this actually boils down to the fact that the index is odd. If you take a negative number to an odd power, so you're multiplying an odd number of negatives, that's going to leave your result as a negative. So when the index is odd, like 3, you can take the root of a negative. Okay, now where this will be an issue is if I say take the square root of -4. Remember, since I've written no number as the index, that means that the index is 2. It's a square root. So that means its even index. This does not exist. At least not as a real number. Because if I try to multiply 2 by itself, that gets me +4, not -4. And if I try -2 instead, squaring that, well, a double negative also gives you a +4. Therefore, whenever the index is even, you're not allowed to take a root of a negative. So you can never take the square root of a negative, if you're dealing with real numbers, that is. Same with fourth root, sixth root, eighth root. We don't deal with those too often. Let's do part D. The fourth root of 16. All right, well, before I write that answer, let's think about it this way. I want to say 2 because 2 to the fourth is 16. Well, that's a very good instinct. Well, the thing is, -2 to the fourth actually gets you in the same place because I'm taking it to an even power. So this is what I was talking about when I said if there are 2 roots, you choose the positive one. So we want just one answer. I choose 2 since positive. That's just the rule we've decided upon. So technically -2 works as well, but we just go with 2. There is a connection to exponents besides this being the reverse process. You can actually frame these as exponents themselves. Let's define b to the 1 over n, assuming n is positive. This is the nth root of b. So radicals you can always express as exponents, these rational exponents, fractional exponents. Quick example. If I take 27 to the 1/3 power, that means the same exact thing as the cube root of 27, which we saw is 3. Now, why would I want this? Well, it turns out that this can be convenient at times because you can use exponent rules to your advantage. So more generally, and before I was dealing with fractions where the numerator was 1, but what if I want, oh, sorry, I actually want, not that it's a big deal, but M is an earlier letter, so let's write that first. So now I can do something with any fraction, M over N, if I use exponent rules to my advantage. Right, in this case, I multiply the powers, 1 over N times M, and that gets me back to this M over N. But there's actually something else I can do. Notice that I can just as well do this. Switch the positions of M and 1 over N, and the same rule works. So these are both valid. And now I'm just going to rewrite these in terms of roots. That's the nth root of B, then taken to the M power. Right, these are connected. And this one can also be rewritten. So nth root on the outside and B to the M in there. So these are the exact same thing. And which way you choose to write it in depends on convenience. What's convenient in the moment? So let's do an example. First off, we want to assume some numbers A and B are positive. Then we want to simplify the following. I want to have it in some form as some coefficient, some number M, times A to a certain power, that's alpha, the Greek letter that corresponds to A, just A to some power, times B to some power, call it beta. And let's put a colon. Here's the thing we're going to simplify. And this is a fraction. In the numerator, we have 81 to the 3/4 power times A to the negative 7/6 times B to the 2/5 over 3 times A to the 5/6 times B to the negative 3/5. Now, just for sorting purposes, I want to separate the constant portions and the A portions in B. Categorizing things a bit. 81 to the 3/4 power. So that's something specific that we can compute. We can frame it like this. It's 81 to the 1/4 power. I'm even going to go ahead and write it as a fourth root. Then cubed. And this is convenient. It's convenient to do it in this way because 81 has a nice fourth root. make that 4 look a little better. 81 has a nice fourth root. Remember, 81 is 9 squared, and 9 is 3 squared. So when you really break it down, it's 3 times 3 times 3 times 3, or 3 times itself 4 times. So the fourth root of 81 is 3. Let's take care of these real quick. The a portions, I can just use the exponent rules we learned last time. Subtract those powers. And over here with the b, I'm subtracting a negative. So as I said, the fourth root of 81 is 3. And we could go ahead and do a little canceling. Right, cancel off one of those 3's from the top. Well, I've got common denominators here. That's great. So I just subtract the numerators. Gets me negative 12 over 6. And again, with the b, I have common denominators. I'm subtracting a negative. So this works out well. I'm left with the 3 squared in the numerator, and the denominator goes away for that first fraction. Negative 12, 6 reduces to negative 2. And b, 5 over 5 reduces to 1. And that's it. Now we actually are done because the problem did not say to use positive exponents only, but rather it said to have it in this form, which we have. So we are done. Next, let's take the square root of w times the ninth root of w and try to simplify that. Well, it's going to help to reframe these as rational exponents. So reframe the square root as w to the 1/2 times w to the 1/9. And now I can use exponent rules now that I've done this. This is where you add the powers. Now, a little tedious, we have to find common denominators. Well, that common denominator is going to be 18. That's the least common multiple of 2 and 9. That's just the product of 2 and 9. So a 9 over 18 plus a 2 over 18 gets me w to the 11 over 18. Okay, now I'll reframe this as the 18th root of w to the 11. And that's the simplest it gets. So exponent rules came to the rescue. Now here's something that one might affectionately call the freshman's dream, where it's something that you want to be true, but it turns out that it doesn't work mathematically. No offense to the freshmen out there, of course. That's just the common name for such a thing. the cube root of x cubed plus y cubed. Now this is not the same thing as x plus y, meaning I'm not allowed to take the cube root of this piece plus the cube root of this piece. It doesn't work like that. The reason is because this is addition. So with addition or subtraction, you're not allowed to split that radical. Let me just say we can't distribute radical over addition or subtraction. It's a common temptation, but don't do it. It's wrong. So let me demonstrate why that's wrong with a little example. Let's take the square root of 5 squared plus 12 squared. First, I'm going to solve this normally the right way by calculating that part inside the square root. We have a 25 plus 144 in there. So that's the square root of 169 when you add those together. So this is all perfectly legitimate, what I'm doing. And 169 has a nice square root of 13. Now let me show you if we were to split that square root, like we may have been tempted to do. Well, the square root and the squares, they cancel. And we get 17. Well, that's not the same number as 13. So this gets you a different answer. So the above part was correct, but you're not allowed to split a square root over addition like this, or any kind of root for that matter. Now the good news is that the radical does distribute over multiplication or division. And we're going to use that. Let's see this in action. Excuse me. Say I want to take the square root of 20 and I want to simplify. The way to do it is to factor 20 as 4 times 5. And now I'm allowed to split that square root over the multiplication. So it's a product of two separate square roots. And 4 has a nice square root. 5 does not. 5 is prime. So this is the simplest it gets, 2 times the square root of 5. Okay, so I want to end with this conjugate. Pardon my writing. So often when we have a fraction with radicals, so you've got radicals either in the numerator or denominator, and usually in this sort of problem, it's just going to be one of those. we want to get rid of them. Now, the fancier name would be rationalize. So rational means polynomial over polynomial, and radicals are not polynomials. So that's why we use this term, rationalize. Okay, so we want to rationalize or get rid of the radicals on one side of the fraction. Oftentimes it's the denominator that we want to rationalize, but you can see it the other way as well. So we'll do an example. How do we do this? Let's look at 9 over the square root of x plus the square root of 3. So I have radicals on one side of the fraction. I want to rationalize the denominator. So in other words, have a polynomial be in the denominator instead of radicals. So integer powers. So the trick is to multiply by something. Denominator. Multiply the denominator, and you have to then do it to the numerator as well. You have to do it to both. By what's called the conjugate. Of this radical expression. The conjugate is something that's designed so that when I multiply by it, these radicals will go away, or these square roots in particular. Right, so the conjugate it's the same thing, but you change the sign. So the sign that's between the two radicals. So now it's the square root of x minus the square root of 3. This is the conjugate of root x plus root 3. This is the thing that we want to introduce. So here's the original. And I want to multiply by the conjugate, just flipping the sign to a minus. And I have to do the same thing above as well, so that I'm not really changing the problem. So the numerator, not really a whole lot we can do. I just want to leave it as this, really. But the denominator, we're going to have to FOIL out. We're taking this times this. So that's FOIL. So first would be square root of x times square root of x. That gets me x. Okay, then the outer terms, I have a root x times a negative root 3. So let's just put the minus out here. And because it's times, I can combine that as just a single radical. So 3x in there. Then the inner part of the FOIL gets me a plus root 3x. And then last, it's going to be the square root of 3 times negative of the square root of 3. Together, that will be a minus 3. And notice that these cancel when I add them together. So that's the purpose of the conjugate, is to get rid of radicals in the denominator. And this really only works for square roots in particular. But this is the type of problem that you'll see. So now the denominator is rationalized just like we wanted. It's just a polynomial now. Now to do this, we had to unrationalize the numerator, but there's really no avoiding that. So we did the problem, we're done. So that's it for the review chapter in the first 2 weeks of the course. So I'll see you next time when we get to lines a little more in depth.